Pacemaker timing cycles. Pacemaker timing cycles is one of the more difficult topics to understand when learning the basics of pacemakers. It's not all that hard to learn the names and functions of the timing cycles, but rather it's how they sometimes interact with each other that can get to be a bit tricky. Now when you get right down to it, a pacemaker is really a bunch of timers or clocks that are running telling the pacemaker when to do something and when not to do something. The two primary functions of a pacemaker are pacing and sensing. The timing cycles really apply to these two primary functions: when to pace, when not to pace, when to sense, and when not to sense. Let's start with single chamber timing. The first timing cycle that we're going to learn about is the lower rate limit. The lower rate limit is often abbreviated LRL. The lower rate limit is the base rate, or the slowest that the pacemaker will allow the patient's heart rate to go. It restarts with each paced or sensed beat. Each beat will show up in one of two ways depending on the program mode of the pacemaker. The first is sensing. If the patient has an intrinsic heart rate faster than the programmed lower rate limit, then the pacemaker will inhibit pacing and sense, but the intrinsic rate must be faster than the lower rate limit. The second is pacing. If the patient doesn't have an intrinsic rate faster than the lower rate limit, then the pacemaker will pace at the lower rate limit. Before we go any further, I want to point out that pacemakers think in milliseconds, so we need to be able to convert beats per minute to a millisecond interval. No problem, just a little simple math here. There are 60,000 milliseconds in 1 minute. So if we take 60,000 and divide that by our beats per minute, we would get our time interval in milliseconds. In this example, the beats per minute is 60, so we take 60,000 milliseconds divided by 60 beats per minute, and we get 1,000 milliseconds. We can also do this in reverse. We take 60,000 divided by our timing interval of 1,000 milliseconds, and that would give us 60 beats per minute. In a single chamber pacing mode, there are always two timers running: the lower rate limit and the refractory period. The refractory period is a period of time following a paced or sensed beat in which the pacemaker will see a sensed event but will not respond to those sensed events. So why wouldn't we want to respond to a sensed event? The answer is, not all sensed events are real physiologic events. Pacemakers are working in millivoltage. That's really sensitive. It's possible that the pacemaker could see a signal such as a T wave or a QRS and interpret that as a P wave on the atrial lead. A T wave could be interpreted as a QRS. The refractory period is really a safety type of feature where the pacemaker says, I see this particular event, but I'm going to ignore it. Because it occurred during this time frame, it's most likely not a true event that I'm looking for. There are three refractory periods: ARP, which stands for atrial refractory period and is used in AAI pacing; PVARP, which stands for post-ventricular atrial refractory period. This refractory period is used in dual chamber pacing, so we'll be talking about that more in just a bit. VRP, which stands for ventricular refractory period. Let's look at VVI pacing and how the timers work. In VVI pacing, we have two timers running: the ventricular refractory period and the lower rate limit. First, we see a V pace. With the V pace, we start our two timers, the ventricular refractory period and the lower rate limit. The ventricular refractory period starts telling us to ignore any sensed events during this time because they are most likely not events that we are interested in, such as T waves. If we look closer at that first beat, the pacing pulse would be labeled as a ventricular pace. Shortly after, the T wave could potentially be labeled as a ventricular sense, but because it lands in the ventricular refractory period, this T wave will be ignored. Below the ventricular refractory period, we have the lower rate limit. The lower rate limit tells us when we need to pace in the ventricle again if a sensed beat doesn't come in first. The lower rate limit timer expires or times out, and therefore we V-pace again, which starts our timers over again. The ventricular refractory period to cover up any events that we don't want to pay attention to, and the lower rate limit telling us when to pace again. The lower rate limit times out, and therefore we pace in the ventricle, restarting our timers. If you'll notice the next beat, we have an intrinsic beat that came in prior to the lower rate limit expiring. This intrinsic event was sensed, and our timers were restarted. When you have an intrinsic event that comes in prior to the lower rate limit expiring, that intrinsic event is often referred to as an escape beat, and the interval that starts with the escape beat is known as an escape interval. Once again, our lower rate limit times out, and therefore we V-pace, starting our timers again. AAI pacing. With AAI pacing, we have two timers, the atrial refractory period and the lower rate limit. First, we see an atrial pace, which starts our two timers. The atrial refractory period starts to cover up any events that we don't want to see, such as the QRS or maybe even the T wave. The lower rate limit starts, telling us when we need to pace in the atrium again. The lower rate limit times out, and therefore we atrial pace, starting our timers once again. Next, we see an intrinsic P wave that comes in prior to the lower rate limit timing out. That P wave is sensed, and therefore we start our timers. Since it was an intrinsic P wave that came in prior to the lower rate limit expiring, it's known as an escape beat, and this interval starting with the escape beat is known as the escape interval. Next, we see the lower rate limit timeout without an intrinsic P wave, and therefore we pace, starting our timers over again, the atrial refractory period and the lower rate limit. Dual chamber timing. There are several timing cycles in dual chamber pacing. It's easier if we break it down into three primary timers first. The time that it takes from one beat to the next beat is known as a cycle. There are three different timing cycles that make up each cycle length. The V to V timer, which is basically your lower rate limit, the AV timer, which is your AV delay or PR interval, and the VA timer, which tells us how long after a V pace until we should pace in the atrium again. When you're programming a pacemaker, you'll enter a lower rate limit and an AV delay, but what you won't enter is VA time. The pacemaker will use the lower rate limit and the AV delay to automatically calculate the VA time, but you may have to calculate it manually when you're troubleshooting the pacemaker at times. Since these three timers make up one complete cycle, we can use any two of them to figure out the third. The V to V time equals your AV delay plus your VA, the AV equals your V to V timer minus your V to A, and your VA equals your V to V minus your AV. Let's go through a couple of examples real quick. If we have a device programmed to 60 beats per minute with an AV delay of 200 milliseconds, then what is our VA time interval? First off, we need to convert beats per minute into milliseconds. So we take our 60,000 milliseconds, divide it by 60 beats per minute, and we get 1,000 milliseconds. Next, we take that 1,000 milliseconds minus the 200 millisecond AV delay, and our VA time is 800 milliseconds. Let's do one more real quick. Now let's say we have a pacemaker programmed to a lower rate of 75 beats per minute and an AV delay of 150 milliseconds. What is the VA time interval? Once again, we take our 60,000 milliseconds, divide it by 75 beats per minute, which gives us 800 milliseconds. Then we take our 800 milliseconds, subtract our 150 millisecond AV delay, and we get a VA time of 650 milliseconds. Remember, there are 4 patterns to dual chamber pacing, so let's look at how these timers function in each of those patterns. AV sequential pacing, or A pace, V pace. First, we see an atrial pace. With this atrial pace, we start our AV delay. The AV delay times out, and therefore we pace the ventricle, which starts our other 2 timers. The VA timer, telling us how long after a ventricular pace till we need to pace in our atrium again. With the ventricular pace, we also start our lower rate limit. Now, devices can be either ventricular-based timing or atrial-based timing. With ventricular-based timing, we're starting a clock with the ventricular pace, telling us when we need to pace in the ventricle again. If the device were atrial-based timing, that clock would start with the atrium, telling us when we need to pace in the atrium again. So next you'll notice that the VA interval has timed out, telling us that we need to pace again in the atrium. So we pace in the atrium, start our AV delay, which times out as well, and so we pace in the ventricle. Once again, our VA interval times out, and so we pace in the atrium, start an AV delay, which times out as well, and so we pace in the ventricle. And this process will just continue on and on. Next, we have complete inhibition, or A-sense, V-sense. Here we see an intrinsic P wave that is sensed, and therefore we start our AV delay. Notice the last part of the AV delay is shaded a different color. That's because we have an intrinsic ventricular event that came in before the AV delay timer expires. This intrinsic event is sensed, and so we start our VA interval and our lower rate limit. The VA interval tells us when we need to pace in the atrium again if a sensed event doesn't come in first. In this example, the next intrinsic P wave comes in before the VA timer times out. Below that, we have the lower rate limit telling us when we need to pace in the ventricle again, which is beat by an intrinsic event that comes in before the lower rate limit expires. With the next intrinsic P wave, we start our AV delay, which is beat by another intrinsic ventricular beat, starting our VA timer and our lower rate limit. The VA interval is beat by another intrinsic P wave, which starts our AV delay, which is beat by another intrinsic ventricular event, starting our VA time and our lower rate limit. Once again, an intrinsic P wave comes in before our VA interval expires, and so we start our AV delay, which is beat by another intrinsic ventricular event, starting our other two timers. Atrial pacing with intrinsic AV conduction, or A-pace V-sense. First, we see a paced atrial beat. With this pacing pulse, we start our AV delay, which is beat by an intrinsic ventricular event. The ventricular event is sensed, and therefore we start our VA interval and our lower rate limit. Next, we see that our VA interval has timed out, telling us that we need to pace in the atrium again. And so we pace, and with that pace, we start our AV delay, which is beat by another intrinsic ventricular event. With the sensed intrinsic ventricular event, we start our other two timers, our VA interval, and our lower rate limit. Once again, the VA interval times out, telling us we need to pace in the atrium, which starts an AV delay, which is beat by another ventricular sense, starting our VA interval and our lower rate limit. Notice once again that our VA interval times out, telling us to pace in the atrium, which starts our AV delay, which is beat again by an intrinsic ventricular event, which starts our VA timer all over again and our lower rate limit. Atrial sensing with ventricular pacing, or P-wave tracking. First, we see an intrinsic P wave that comes in. With that P wave, we start our AV delay, which times out, and so we pace in the ventricle, starting our VA interval and our lower rate limit. This time, the VA interval is beat by another intrinsic P wave that comes in, which is sensed, and therefore we start our AV delay, which times out, and so we pace in the ventricle, starting our VA interval again and our lower rate limit. Now, something that I'd like to point out, if you look back at the previous cycle length, the lower rate limit never timed out, but yet we paced in the ventricle. The reason for this was because we had an intrinsic P wave that came in, starting the AV delay that timed out, forcing us to pace in the ventricle. Once again, the VA interval is beat by another intrinsic P wave, starting our AV delay, which times out, and so we pace in the ventricle. One more time, the P wave comes in before the VA interval times out, which starts our AV delay, and so we pace in the ventricle, starting our VA interval and our lower rate limit again. Blanking period. The blanking period is an interval of time where the pacemaker disables its sensing amplifiers after a pacing pulse. The purpose of this timer is to prevent crosstalk. Crosstalk is when a pacing pulse from one lead is sensed on the other lead. So you might be asking, why is crosstalk banned? If an atrial pacing pulse is sensed on the ventricular lead, the pacemaker will assume that that signal is a ventricular sense and will inhibit ventricular pacing. In a dependent patient, it would look something like this. A pace V sense, A pace V sense, A pace V sense, lots of P waves, and no QRSs. So how does a pacemaker fix this problem? Well, the pacemaker has two blanking timers for when we pace. If we pace in the ventricle, we will A blank. It's easier if we think of it as A blank after ventricular pace. This is a blanking timer for the atrium, but it occurs after ventricular pacing. Here you see an AV sequential paced beat. Starting with the ventricular pace, then extending out for a short period of time, we turn off the sensing amplifier on the atrial lead to make sure that we don't sense any ventricular pacing pulses on the atrial lead. If we pace in the atrium, we V blank. It's easier if we think of it as V blank after atrial pace. This is a blanking timer for the ventricle and occurs after atrial pacing. Here we see the same AV sequential pace beat. This time, we have our V blanking timer start with the atrial pace extending out a short period of time where the sensing amplifiers in the ventricle are turned off so we don't oversense any atrial pacing on the ventricular lead. We only have A blank and V blank timers for when we pace in the other chamber. URL, which stands for upper rate limit. It might also be referred to as maximum track rate or MTR. This timer really serves as a maximum speed limit for how fast the pacemaker can pace the heart in response to an increased atrial rate, or in other words, P-wave tracking. The purpose of limiting how fast we can P-wave track is really a safety feature to make sure that if our patient goes into an atrial arrhythmia, such as atrial fibrillation, that we don't pace the ventricle at 250 beats per minute in response to that atrial fibrillation. Maximum sensor rate, abbreviated MSR. This timing cycle is for modes ending in R, such as DDDR and VVIR. This is used when the pacemaker is pacing the heart at an increased rate in response to the pacemaker sensors. It is the maximum rate that the pacemaker is allowed to pace at in response to what the rate response sensors are indicating. Here's an example. First, we see a ventricular pace. Now the rate response sensors could be telling the pacemaker to pace here, but because our maximum sensor rate timer hasn't timed out yet, we're not allowed to pace. Once the max sensor rate timer expires, we pace in the ventricle, and then shortly after that, the sensors could be telling the pacemaker to pace again. But because our max sensor rate timer hasn't expired again, we have to wait. Rate response sensors don't work the same way in every patient. A setting that works well for one patient may not work well for another. The maximum sensor rate is a safety feature designed to limit how fast the pacemaker can pace the heart according to the sensors in case the sensors become overly aggressive. Okay, back to some AV sequential pacing to see what all these new timers look like. First, we see an atrial pace, which starts our two atrial-based timers, our AV delay and our V blanking. Remember, we V blank after A pace. Next, we see that the AV delay timer has timed out, and so we pace in the ventricle, starting the rest of our timers. We have the A blank after V pace, PVARP, which stands for post-ventricular atrial refractory period. Now the name describes it quite well. It's a refractory period for the atrium, but it starts after a paced or a sensed ventricular event. The VA interval telling us how long after the ventricular pace till we need to atrial pace again. V refractory, our upper rate limit, and our lower rate limit. Our VA interval times out again, telling us that we need to pace in the atrium. With the atrial pace, we start our atrial-based timers, the AV delay, and the ventricular blanking. The AV delay times out again, telling us we need to pace in the ventricle, which starts all of our ventricular-based timers, our A blanking, PVARP, VA interval, ventricular refractory upper rate limit, and lower rate limit. Once again, our VA interval timers expire, telling us that we need to pace in the atrium again. With that atrial pace, we start our timers. The AV delay expires, telling us we need to pace in the ventricle, which starts our ventricular timers again. And this process will just continue on. Upper rate behavior. With all these timers going, telling the pacemaker when to pace and when to sense, you're bound to have some timers that overlap and interact with each other. There are some scenarios where if certain sensing happens during the right timer, some funny pacemaker behavior will occur. This behavior is known as upper rate behavior. This behavior only happens when you're P-wave tracking at the upper rate limit or the maximum track rate. It's important to know that this is not a malfunction of the pacemaker, but rather it's a fact that the pacemaker is bound by certain rules that it must follow, making it appear as if there is something wrong with the pacemaker, when in actuality it's normal pacemaker function. The trick is to program the pacemaker to minimize any upper rate behavior. There are three types of upper rate behavior: 2-to-1 block, pacemaker Winky-Bach, and pacemaker-mediated tachycardia, abbreviated PMT. Upper rate behavior occurs when the pacemaker is P-wave tracking and an intrinsic atrial beat happens before one or more of the following timers times out: the P-VARP, the TARP, or the upper rate limit or maximum track rate. We haven't talked about TARP yet, but it's a pretty simple timer to understand. It's really just the AV delay plus the P-VARP, which stands for our total atrial refractory period. Here is an example of 2-to-1 pacemaker block. If you look closely at the rhythm, you'll see that every other P wave doesn't have a QRS. So why would the pacemaker only ventricular pace after every other P wave? Well, let's take a little closer look at the timers to see what's going on in this rhythm strip. The first thing that we see is an intrinsically conducted P wave. With that P wave, we start our AV delay. The AV delay times out and we pace in the ventricle. With the ventricular pace, we start our P-VARP and our maximum track rate. Now after the sensed P wave, the pacemaker is also running the TARP timer, which again stands for total atrial refractory period and is nothing more than the AV delay plus the P-VARP. If we were to move the P-VARP or the TARP timer up onto the rhythm strip, we can see that the second P wave lands before the TARP timer expires. If we look back at what the refractory period is, it's a period of time following a paced or sensed beat in which the pacemaker will see sensed events but will not respond to those sensed events. These P waves will be sensed and labeled AR, which means atrial sense in refractory, or AS in parentheses. The parentheses also mean that it's an atrial sense occurring in refractory. Next, we see a P wave come in that's sensed, and so we start our AV delay again. This AV delay timer times out, starting our other timers. Once again, you can see that our next P wave lands in the refractory period, and therefore we can't start an AV delay again. But shortly after that, the next P wave is sensed, and so we start our AV delay. The AV delay times out, and we pace in the ventricle, starting our other timers again. This 2-to-1 pacemaker AV block will continue on until the patient's sinus atrial rate slows down to the point so that every P wave lands outside of refractory. The one good thing about 2-to-1 AV pacemaker block is that it's really easy to figure out exactly when it will happen. Remember, the TARP is the total atrial refractory period and is the AV delay plus the P-VARP. The way we calculate the 2-to-1 block point is we simply take 60,000 milliseconds and divide it by our TARP. Let's go through a couple of quick examples. Let's say you have a pacemaker programmed with an AV delay of 200 milliseconds, a P-VARP of 300 milliseconds. That gives us a TARP of 500 milliseconds. So we take 60,000 milliseconds and divide it by 500 milliseconds, and that gives us a 2-to-1 block point of 120 beats per minute. Now let's say you have a pacemaker program with an AV delay of 120 milliseconds, a P-VARP of 340 milliseconds. That gives us a TARP of 460 milliseconds. So we take our 60,000 milliseconds, divide it by 460 milliseconds, and it gives us a 2-to-1 block point of 130.4 beats per minute. Pacemaker Winky Bach. As the sinus rate increases, P waves can start to sense before the maximum track rate timer expires. Remember, the maximum track rate is the fastest rate at which the pacemaker can pace. So if an atrial sense happens before the maximum track rate timer expires, the pacemaker must wait to pace the ventricle by extending the AV delay. Eventually, the P wave could arrive soon enough that it lands within the refractory period, causing the pacemaker to ignore that signal. If the atrial sense signal is ignored, then no AV delay will be started and no ventricular pace will occur and will result in a dropped beat. So what does this look like? First, we see an intrinsic P wave, which starts an AV delay. The AV delay timer times out, and so we pace in the ventricle, which starts our P-VARP. Next, we see another intrinsic P wave, which starts another AV delay. The AV delay times out, and we should have paced the ventricle here, but we didn't. So the question is, why not? The reason is the max track rate timer is running and hasn't timed out yet. Remember, the max track rate is the fastest that the pacemaker can pace. Therefore, the pacemaker has to wait until the max track rate timer expires, and then it can pace in the ventricle, which creates a lengthened AV interval. Now that we've V-paced, we can start our P-VARP again. Notice how much longer the TARP is in this cycle compared to the last cycle. Here's an example of 4 to 3 pacemaker Winky-Bach block. Notice the gradual lengthening of the AV delay until the QRS is eventually dropped, just like a real second-degree AV type 1 Winky-Bach block. Let's take a closer look at what's going on with these timers during this rhythm strip. First, we see an intrinsic P wave. The P wave is sensed, and so we start an AV delay. AV delay times out, and we pace in the ventricle, which starts our ventricular timers. A short time later, we see another P wave that comes in, the P wave is sensed, and so we start our AV delay. The AV delay times out, but we're forced to wait a little bit because our maximum track rate hasn't timed out yet. As soon as the maximum track rate timer expires, we pace in the ventricle, which starts our ventricular base timers again. Shortly after we pace in the ventricle, another intrinsic P wave comes in. The pacemaker senses that P wave and starts an AV delay. The AV delay times out, and we can't pace in the ventricle because we're forced to wait until our maximum track rate timer expires. Once our maximum track rate timer expires, we pace in the ventricle, which starts our ventricular timers again. Soon after the ventricular pace, we have another intrinsic P wave that comes in. Notice that this P wave lands inside of PVARP. This means that we've sensed the P wave, but since it landed inside a refractory, we're going to ignore it, and we won't start an AV delay, which will result in a dropped paced ventricular beat. Not too long after the dropped paced ventricular beat, we see another intrinsic P wave comes in. This P wave is again sensed, and so we start our AV delay. AV delay times out, and we pace in the ventricle. And this cycle will continue on again and again, with every fourth P wave landing in refractory, resulting in a 4 to 3 pacemaker Winky-Bach block. Generally speaking, we're going to want to avoid upper rate behavior. Where this gets a bit tough is when we have a long AV delay, a long PVARP, and a low max track rate. Shortening the AV delay and PVARP and increasing the max track rate is the best way to fix upper rate behavior. What we would hate to have happen is to have a patient with a 2-to-1 block point at the same rate or even maybe a lower rate than their maximum track rate. Sometimes we can't avoid upper rate behavior because of how we want to set the pacemaker. So if we can't avoid it, we can certainly try and minimize it. Also, I wanted to mention that generally Winky-Bach block is preferred to 2-to-1 block. So ideally, if we're programming a patient, we want to set them up so it looks something like this. As our sinus rate increases, from our lower rate limit to our maximum track rate, we should have 1-to-1 conduction. And from the maximum track rate up to the 2-to-1 block point, we'll Winky-Bach block. Beyond that, we're going to have 2-to-1 block. Let's go through an example. Remember, our 2-to-1 block point is 60,000 milliseconds divided by our TARP. Now let's say we have a patient programmed with an AV delay of 200 milliseconds, a PVARP of 300 milliseconds, and a maximum track rate of 140 beats per minute. First, we need to figure out our TARP. So we take 200 plus 300 and we get a TARP of 500 milliseconds. Next, we take 60,000 milliseconds, divide it by 500 milliseconds, our TARP, and we get a 2-to-1 block point of 120 beats per minute. Wait a minute, this is no good. If you look closely here, our 2-to-1 block point is less than our max track rate. This scenario would look something like this. From our lower rate limit up to 120 beats per minute, we'd have 1-to-1 conduction. Anything above 120 beats per minute, and we'd have 2-to-1 block. So this patient is in need of some reprogramming. So let's change our AV delay from 200 milliseconds to 120 milliseconds, and change our PVARP from 300 milliseconds to 280 milliseconds, and we'll leave our max track rate at 140 beats per minute. So next we need to figure out our TARP, so we take 120 plus 280, which gives us 400 milliseconds. Now we take 60,000 milliseconds, divide it by our 400 millisecond TARP, and we get 150 beat per minute 2-to-1 block point. With our new programming, it would look something like this. From our lower rate limit up to our max track rate of 140 beats per minute, we would have 1-to-1 conduction. From 140 beats per minute to 150 beats per minute, we're going to end up with Winky-Bach block. Anything above 150 beats per minute will have 2-to-1 block. Upper rate behavior only happens when we're P-wave tracking, so another way to deal with upper rate behavior is to use rate response. Rate response is any mode ending with the letter R. If rate response is on and the patient hits a 2-to-1 block point, the pacemaker will start pacing the heart at the sensor indicated rate. On a side note, the sensor indicated rate will most likely not be as fast as the patient was P-wave tracking, but it still might be better than going to 2-to-1 block. For example, let's say a patient was P-wave tracking until they hit their 2-to-1 block point of 120 beats per minute. This means as they're tracking up to 120 beats per minute, they're 1-to-1. As soon as they hit 120, they'll go to a 2-to-1 block point. If rate response is on, the patient will start pacing according to what the sensors are saying. In this example, let's say that the sensor indicated rate is 90 beats per minute. So once the patient hits 120 beats per minute, instead of 2-to-1 blocking down from 120 to 60 beats per minute, the pacemaker would pace at 90 beats per minute. Pacemaker-mediated tachycardia, abbreviated PMT. PMT is a tachycardia caused by the pacemaker, wherein the pacemaker is tricked into thinking it is P-wave tracking at or near the upper rate limit. This tachycardia is an endless loop and requires an outside interaction to break that loop in order to stop the tachycardia. It will appear as ascents V-pace at or near the maximum track rate or upper rate limit. Here's an example EKG of a patient in a PMT. At first glance, you might say that looks pretty normal. Patient is atrial sensing and V-pacing at about 120 beats per minute. The problem is, the patient's been at rest for a long time, is short of breath, and feels miserable. So what's going on here? To understand what a PMT is, we need to take a look at what the heart's normal conduction is. So in normal conduction, the SA node starts the heartbeat cadence. The SA node sends out an impulse that travels through the interatrial pathways, down to the AV node, down through the bundle of His, and down the bundle branches. This conduction is known as antegrade conduction. When something like a PVC happens, a patient can have abnormal conduction. If a PVC were to originate in the left ventricle, that impulse could travel up the bundle branches, through the bundle of His backwards into the AV node, then into the interatrial pathways, causing the atrium to contract. This backwards conduction is known as retrograde conduction. So back to our rhythm strip. Let's take a little closer look at what's going on. Somewhere buried at the end of the T wave, there's an atrial sense. This atrial sense is actually a retrogradely conducted P wave. Since this P wave is sensed, we start an AV delay, and that AV delay times out, and we pace in the ventricle. This ventricular pace actually causes a retrogradely conducted wavefront, which causes another retrograde P wave. The P wave is sensed, and so we start an AV delay, which ends in another V pace, which causes another retrogradely conducted P wave. That P wave is sensed, and so we start an AV delay that times out, and we pace in the ventricle. The ventricular pace causes another retrograde wavefront, causing another retrograde P wave that is sensed, that causes another AV delay, which causes another V pace. This process will continue until something breaks the retrograde conduction cycle. In order for a PMT to be possible, there are 3 conditions that must be met. The pacemaker must experience a loss of AV synchrony. The patient must have intact VA retrograde conduction, and the patient's VA conduction time must be greater than the programmed PVARP. Let's look closer at loss of AV synchrony. A loss of AV synchrony and retrograde conduction has several causes: a PVC, an oversensed P wave, an undersensed P wave, loss of atrial capture, magnet application, magnet removal, threshold testing, and electromagnetic interference. So now that we know a little bit more about PMTs, the question is, how do we stop or prevent a PMT? To figure this out, we need to go back to the 3 conditions that must be met in order for a PMT to be possible. If you look at those 3 conditions, the only one that we really have control of is number 3. The patient's VA conduction time must be greater than the programmed PVARP. Let's look at a little example here. First, we see a retrogradely conducted P wave. That P wave is sensed, and so we start an AV delay that times out, and then we V pace. With that V pace, a retrograde conduction wavefront starts, causing the next retrograde P wave. Now let's take a look at the effect that P-VARP has on a PMT. If we take our P-VARP and move it up, we can see that that next retrogradely conducted P wave lands just outside of the P-VARP. So what we want to do is extend our P-VARP just a little bit so that the next P wave lands inside of the P-VARP. Since that retrogradely conducted P wave lands inside a refractory, no AV delay will be started, and no V pace will occur, causing the next retrogradely conducted P wave. As a result, the patient will most likely have an atrial sense or an atrial pace that comes in, reestablishing AV synchrony. Okay, so back to how do we stop or prevent a PMT. People usually have a very consistent retrograde conduction time. So what we want to do is measure the patient's retrograde conduction time. If we look back to our EKG strip of a PMT, we want to find a ventricular pace. From that ventricular pace, we measure to the next atrial sense. That time interval is our retrograde conduction time. Now that we know our retrograde conduction time, we want to program a P-VARP longer than that retrograde conduction time. Another thing that we can do is use programming features such as PMT termination algorithm and P-VARP extension after PVC. Now I'm not going to go into any more detail about these programming features such as PMT termination algorithm because every company's algorithm is just a little bit different. Okay, so I need to back up a little bit. Earlier I know I said the upper rate behavior only happened when P-wave tracking at the upper rate limit or the max track rate. But when I was talking about PMT, I also said it will appear as a sense V pace at or near the max track rate or upper rate limit. I wanted to be sure that I mentioned there are a few situations where a PMT can occur below the max track rate or the upper rate limit. If the patient has a long enough retrograde conduction time, it's possible that the PMT can occur below the upper rate limit. That's it for pacemaker timing cycles. Now, once again, I wanted to gear this presentation towards someone that is new to pacemakers. There's a lot more detail that we could have gone into. Anyways, I hope that you found it interesting and useful.